Let us discuss this question. That is question number 2.10 in electrochemistry. This is your exercise question. So they had given the data of a conductivity of sodium chloride at 298 Kelvin. That is the concentration as well as the kappa value they had given. They asked us to calculate the molar conductivity for all concentrations, and we have to draw a graph between the molar conductivity and square root of the concentration. And finally, we have to find out the limiting molar conductivity, right? So let us start. First, they had given the concentration, right? Concentration I'm writing here is, they had given us 0.001. This can be done 10 to the power of minus 3 for simplification. And they had given kappa. And what you have to understand, the value given here is kappa when multiplied by 10 to the power of 2 in Simon per meter, right? If we need the kappa value alone, what we have to do? We have to multiply this value into 10 to the power of minus 2. So this can be written as 1.237 into 10 to the power of minus 2. This is a real kappa value in Simon per meter. Now, usually this kappa value will be taken as Simon per centimeter. Now we are going to convert the value of kappa into Simon per centimeter. So what is Simon per meter? Simon per meter here. So we have to convert it to Simon per centimeter. 1 meter is equal to 100 centimeter. So this is Simon per centimeter. Simon by 100 centimeter. So this can be written as Simon per meter. So that is equal to, this can be written as Simon 10 to the power of minus 2 per centimeter. Am I right? Simon per centimeter 10 to the power of minus 2. So what we have to do to convert Simon per meter into Simon per centimeter, we have to multiply by 10 to the power of minus 2. Got it? Already we had multiplied by 10 to the power of minus 2 to get the real kappa value. Again, this value to be multiplied into 10 to the power of minus 2 to convert into Simon per centimeter. So this can be written as 1.237 into 10 to the power of minus 4 directly. Right? Now we have to go for the value of molar conductivity. Right? Lambda m, that is equal to kappa into 10 to the power of 3, that is 1000 by C. So this can be written as kappa, what is the value? 1.237 into 10 to the power of minus 4 into 10 to the power of minus 3, sorry, plus 3, 10 to the power of plus 3 divided by the concentration part, 10 to the power of minus 3. 10 to the power of minus 3. If we brought the 10 to the power of minus 3 to the numerator, so this value can be written as 1.237 into 10 to the power of minus 4 into 10 to the power of plus 6. Am I right? So this can be finally written as 1.237 into 10 to the power of 2. Finally, we can write it as 123.7. This is a molar conductivity value for 10 to the power of minus 3 concentration. Now, I had made the tabulation for this one, that is concentration for 10 to the power of minus 3. The kappa they had given is 1.237 10 to the power of minus 2. So I had converted into Simon per centimeter. That is 1.237 10 to the power of minus 4. By using the formula, molar conductivity is equal to kappa into 1000 by C. So we get the value 123.7. This is what I worked out. That is the C half value. That is a square root of the concentration, that is equal to 0.0316. So this is the value we worked out. So like this, you have to work out for all concentrations. Given for all concentrations, we have to work out. Right? So now we have to make graph between these two values. That is, what is this? This is a molar conductivity and the square root of concentration. So we will write this in a separate sheet. Right? Just take a screenshot to understand these things. So let's move to the graphical sheet. So this is what. So here we have the molar conductivity value as well as the square root of concentration value. We are going to plot the graph. So the value varies between the square root of the concentration starts from 0.0316 and it ends with 0.316. right? And like that, so that we have the value as 0.05 from 0.05 to 0.35. And here the molar conductivity value varies from 106.7 to 123.7. So let me start with 106 and let me go up to 124. So this is the x and y axis I had made. Let us plot the graph. So let us start with 106.7, that is a 0.316, right? So 106.7 will be somewhere here. So let me start like this, 106.7. So let me have like this here, and this will come around where it ends on. It goes with 0.316, and this is 0.30. Let me have 0.31 here approximately, right? So this is the point. So this is the point we have to mark here. So like that we have to make a graph for 0.224. C of is 0.224 here. This is 0.2 and 0.22 will be somewhere here. And here the x-axis value is 111.1, 111 somewhere here. Right? So it will be somewhere here like this. So like this, next one it is 115.8. Let me have 115 here, 115 here, and 115.8 will be somewhere here. That goes up to here, 115, 115.8, 115.8, and that goes for 0.100, 0.100 here. So likewise, if we make the graph, we will get a straight line like this, right? We will get a straight line. Here one, here one, here one, here one, here one. Right. Now, so this is a straight line graph of molar conductivity versus concentration. We have to go for what we have to identify. We have to go for limiting molar conductivity. So as we know, being a strong electrolyte, NaCl being a strong electrolyte, if we extrapolate this one, we will get the limiting molar conductivity, right? So what is the last value given here? 123.7, right? So this is 123. This line is 123.7. And that goes to 0.0316. This is 0.05. So let me take this 0.03 here. So from here, the line will be here somewhere here. What is this? The end point will be 123.7 here. Inge. The end point will be somewhere here. So if we extrapolate this graph, it will meet somewhere here at 124. So the final graph will be like this. We'll get a straight line, and if we get the extrapolation, we'll get the value 124, right? So the limiting molar conductivity value will be approximately 124 here. So the limiting molar conductivity value will be approximately 124 here.